Hello, and welcome to this NASA briefing about an exciting new discovery scientists have made around Earth's radiation belts. I'm Steve Cole from NASA Headquarters Office of Communications. We're bringing you this briefing today from the Johns Hopkins University Applied Physics Laboratory in Laurel, Maryland. Our panel today is going to talk to you about a new finding that's just been released today that is using data from NASA's Van Allen probes mission, which was just launched last year. Our panel today, we have four panelists. Let me introduce you to them. First is Mona Kessel, Van Allen Probes Program Scientist from NASA Headquarters in Washington. Dan Baker, Director of the Laboratory for Atmospheric and Space Physics at the University of Colorado in Boulder. Nicky Fox, Van Allen Probes Deputy Project Scientist from the Johns Hopkins University Applied Physics Laboratory, and Joe Kunches, space scientist at NOAA's Space Weather Prediction Center in Boulder, Colorado. After our four panelists have given opening remarks, we'll open it up to questions here in the audience, people watching on NASA television, and media on the phone lines. If you're watching on NASA TV, you can ask a question through Twitter by using the hashtag AskNASA. Okay, we'll begin with Mona.
Thank you, Steve. So NASA's radiation belt storm probes launched last year, as Steve said, in August 2012. And right away we went into a 2-month time period of we call commissioning, where the doors open, the booms deploy, the instruments turn on, and we start ramping up the high voltage. What we're trying to do is check out all the instruments, make sure everything's operational. So that was 2 months. As soon as that period was over, then NASA renamed the mission the Van Allen probes. That was in honor of James Van Allen, who launched the Explorer-1 satellite in 1958 that discovered the radiation belts. So if we go to the first graphic, thank you, that shows the famous picture of Pickering, Van Allen, and von Braun holding up the Explorer-1 satellite right after their successful launch. And on the right side is a picture of James Van Allen from Time magazine, and that was because after that mission went and the subsequent missions, he and his team pieced together the information that let us know, or that deduced that there was trapped radiation in the Earth's magnetic field. And so that trapped radiation is now called the Van Allen belts. And so this mission is named in honor of him. But what are they? What are these radiation belts, and where are they? If we go the next, thank you, then you can see this is a schematic. You see Earth in the center. You see the sun off to your left, and you see two red regions. This is a cutaway view. So these are donut-shaped regions that wrap around the Earth. There's an inner belt and there's an outer belt, at least as far as we have understood from the beginning of the explorers. So what happens is there's trapped radiation in those two areas. The inner belt runs from about 1,000 to 8,000 miles above the surface of the Earth, and the outer belt is from about 12,000 to about 25,000. So these satellites travel through these belts all of the time. And you can see some of them pictured up there. You can see the two Van Allen probes. You can see GPS. GPS travels through those regions all the time, even in quiet solar conditions. But when we have disturbed conditions, when there are solar storms, then the belts expand. The inner belt will actually come down into the region where the International Space Station flies and other low-orbiting satellites. And the outer belt expands outward. And so it encompasses the area that we call geosynchronous orbit, where a lot of our communications satellites are. And there's about 300 satellites out there. So these satellites then are in the way of potentially harmful radiation. It can affect their electronics, and it can pose a threat to astronauts and all of our satellites that are there. So the radiation belt storm probes, now the Van Allen probes, was the second mission with the Living with the Star program. Pictured here, this is just a couple of images to give the sense of what the Living with the Star program is about. It's making the connections between the assets from the sun to the Earth that affect life and society. So you can see there astronauts, you can see greenery for plants, you can see there are fisheries there are power systems. All of these things are affected by space weather, as we call it, affected by these radiation belts. So Joe Kunches later in this presentation is going to talk about that a little bit more. And the only thing I still want to tell you now is about the Solar Dynamics Observatory, which was the first mission with the Living with the Star program. I'm going to show you a video. This is right after launch, where a filament from the sun erupts from the atmosphere of the sun out into space. It carries with it, it's a coronal mass ejection that's actually headed towards the Earth. And you can see another picture of it here with SOHO, which is one of our older satellite assets. And this will come back to SDO and show you that again, this filament that bursts out into space. So those happen all the time on the sun, but they're not always directed at Earth. This one was, at least as a glancing blow, and it came to the Earth, and our radiation belts exploded with things that were happening. And so now I'm going to turn this over to Dan Baker and let him tell you about this remarkable discovery.
Thank you, Mona. Yes, I'm going to talk to you today about the science paper that's being published today in the journal Science, actually online, Science Express. I'm going to talk to you about the confinement of these very high-energy particles in Earth's magnetic field. As Mona noted, for the last 5 decades, we've been told in the textbooks that the Van Allen belts consist of 2 regions of trapped radiation, the inner stable zone, slot region, and outer zone. What we found rather remarkable is just a couple of days after turning on our high-energy electron detection instrumentation that we really saw that there was a 3-belt structure, and this persisted for 4 weeks and then really turned off. If I could have the first graphic, please. This is several different energy channels displayed across in time. The vertical axis is essentially distance measured out from the Earth in Earth radii. And if you do the next graphic click here, you'll see that we saw the inner belt, we saw the expected slot region, and then we saw this new emergence of a 3rd belt and a second gap region, a second slot. If we go on to the next slide, or the next animation really, I'd just like to tell you that the relativistic electron-proton telescope was put onto the spacecraft. You see the integration process here. It was really geared toward measuring the highest energy particles confined in the Earth's magnetic field. And what our goal was to really be able to measure to higher energies with better energy resolution, better temporal resolution, better spatial resolution in order to address these very long-standing questions about how particles are accelerated and lost from the Van Allen belts. If I could have the next graphic, please. A further motivation for us was the long run of data that we had from another NASA mission called the Solar Anomalous Magnetospheric Particle Explorer, SAMPEX. This was launched in 1992. It made measurements in low Earth orbit. It was really not operating in the throat of the cosmic accelerator that operates in our neighborhood. But it was really revealing the inner belt, the outer belt, the slot region over a long period of time. We learned early in the summer of 2012 that the SAMPEX mission was going to come to an end. Atmospheric drag was going to bring the spacecraft down and cause its demise sometime in the fall of 2012. And so we went on a campaign to try to turn on our instrument, the REPT instrument, as early as we possibly could after launch. In the normal flow of commissioning that Mona talked about, we would have turned on about 34 days after launch. We really were able to turn on 2 days after launch. And we were very fortunate that we did, because if we go to the next slide, what we saw when we first turned on was that the belt had the 2-belt structure as we expected. And then as time marched on, we saw this emergence of 3 belts. And the lower panel really shows here the kind of collapse of all the orbits onto a single meridional plane. And as you watch this, you can see that this 3rd belt emerges pretty clearly. And then, like a knife edge, the entire outer Van Allen belt is ripped away. And then there's a new emergence of this. And I'll just ask that we go through this again so you can see that sequence again. Here we are seeing the single storage ring feature, as we call it. And then we see the entire outer belt outside that storage ring undergoing all kinds of dynamics. But this storage ring, or torus, is just there very persistently and unchanging for the better part of 4 weeks. We first foolishly thought the instruments were not working correctly, but we quickly realized that that couldn't be true. It had to be a real phenomenon. We've been studying that now. If I could have the next slide, I'd just like to show you then an animation that's been put together by scientists here at the Applied Physics Laboratory in which we've assimilated the data into the models and are now portraying this the way the kind of global radiation belts work. And so what you can see, the sort of on either side there, you see this bright, stable kind of band outside the slot region, and that's the storage ring. The entire further outer part of this is undergoing all kinds of dynamics, but that feature is just there, rock solid for 4 weeks. Very puzzling, very exciting, and as I say, the chance to really rewrite some of the understanding that we thought we had for the past 50 years. So I'll turn it over now to Nicky Fox.
Thank you, Dan. So Dan has presented some really fantastic results, new, exciting results today. And it really goes to show that even after 55 years after the discovery of the Van Allen belts, they are still surprising us. We really thought we knew them, but clearly we didn't. We've always known, as Mona said, that there were 2 distinct belts. We did know that the outer one was very dynamic and responded to these large events coming from the sun, but we had no idea of the structure that was embedded within that outer belt. So it really is a case of the observations leading theory, and certainly the theorists and the radiation belt modelers are scrambling to catch up with these great observations. One of the reasons that I think that there are so many mysteries still in the radiation belts is because they are home to a host of fundamental physics processes that are occurring throughout our universe. The same physics that causes the particles to be accelerated in the Earth's radiation belts also causes radiation belts to occur at all of the large magnetized planets in our solar system. So Neptune, Jupiter, Saturn, Uranus all have radiation belt structures very similar to the Earth. Even outside our solar system, particle acceleration is also causing distant nebula to glow in X-rays. So as we say, it's just rocket science. It's just particle acceleration. It's the same thing that's happening here is happening everywhere. And we're very lucky that we have this region of interest just a few thousand kilometers above our head. It's really rather like having your very own particle accelerator in the backyard. What also, for me, makes this event even more interesting is, as Mona spoke of initially, the sun drove that large storm that actually caused the beautiful event to be kicked off. And as we show here, SDO also caught the event that actually caused the annihilation of the radiation belt. So that knife edge that Dan showed, where you see the outer belt almost disappearing, was also driven by our star, the sun, always the star of the show. So the sun giveth and the sun taketh away. And one of the central themes of the radiation belt storm probes mission is to really see why the radiation belts respond in such different ways to seemingly similar events coming from the sun. And the only way that we can really do that is to really take a system approach and look at everything coming from the sun to our Earth space. And so this animation shows nicely how the radiation belt storm probes, or the Van Allen probes, have now taken their place in the Heliophysics Observatory. So you're seeing a fleet of spacecraft in all the key locations between the sun and all the way to Earth. What makes the radiation belt storm probes so important is that they really have taken their place here. They are designed and developed to go after the physics that is occurring in the radiation belts. So they will really be providing those much needed observations so we can decide what's really happening in the radiation belts. Also on board the spacecraft, we have a full complement of instruments. So in addition to the highest quality particle measurements that have ever been made that Dan has already showed, we also have fields and waves instruments. So we're now going to study all of the wave structures that are maybe responsible for causing that third belt and eroding that center part in the outer radiation belt, which we've termed the second slot region. So we're very looking forward to these great new capabilities we have, not only providing discoveries, but also providing explanation as to why these phenomena are occurring. And also, as Mona said, the practical nature of the effects here at Earth. They are causing dramatic changes in our near-Earth space, which have effects on life and society. We live and work in the radiation belts, and all our technology is based there. So understanding how the radiation belts change is extremely critical for our technological infrastructure. So in addition to the wonderful science that we have with the storm probes, we're also sending down real-time data, real-time space weather data that comes down and is captured through a network of ground stations and then is available within about 30 minutes on the web. And obviously scientists are very excited about these raw data, but we understand that they're not always accessible to the general public. So we actually feed them into models. One really good example is the DREAM model, which is run out of Los Alamos National Laboratory. And we are in the process now of feeding our real-time data into this model, and within the next 3 months we will be delivering that to the NOAA Space Weather Prediction Center, where they'll be using it to better forecast space weather. And that's a good segue to pass on to Joe Kunches from the Space Weather Prediction Center to tell us all about space weather.
Thank you, Nikki. Discoveries from missions such as the Van Allen probes are really the wellspring from which improvements to operational space weather services come. And let me take you into the forecast office of the Space Weather Prediction Center here in a minute and show you what it's like to do operational space weather forecasting. This is the forecast office from NOAA's Space Weather Prediction Center. We operate 24 hours a day, 7 days a week. We monitor space weather and we make the predictions that people want to plan from. We coordinate our activities with the U.S. Air Force. They have their own center at Offutt Air Force Base. And we're the World Warning Agency for 14 countries. The International Space Environment Service is focused at Boulder. Among the data that are used there, along with the GOES data from NOAA, also you'll see NASA data from SDO, from ACE, from Stereo, from SOHO, and also those data feed into models. Here is the Enlil model from the solar wind that we get, and it enables the forecasters to make the best assessment of the current conditions and allows them to give good predictions of the conditions in the near future. In the next slide, I'll show you how one of the ways at which we get the word out from in real time as conditions occur. This is a graph showing in white the progress of the current solar cycle, and in blue the number of subscribers to our email product subscription service. Now it numbers more than 32,000 subscribers. Of those subscribers, about 9,500 characterize themselves as having something to do with satellites. Either they are designers, they're engineers, they're manufacturers, they're operators. So clearly the satellite community is a very important community for us to serve with the best real-time space weather information that we can garner. Now, to focus for a minute on the satellite community, this probably comes as no surprise to anyone, but in the next slide, here's a chart from the Satellite Industry Association which shows the revenues over about the last 5 years. This goes back to 2006. 2011 is the last full year for which the data are available. And what you can see without looking too hard is that its growth, 9% about on average over the last 5 years. But also the last year is about $177 billion worth of revenues, further underscoring the fact that this is a very important customer base that needs the best space weather information they can get. And finally, just to maybe wrap it up, what is it about the space environment and space weather that causes disruptions to satellites? And this really goes to the activities that the Van Allen probes are designed to do. It's charged particles. And on the next slide, there's an illustration of the kinds of things that can happen to satellites by virtue of, say, low-energy electrons, which can do surface charging, or high-energy electrons, which can embed themselves within the spacecraft and cause deep dielectric charging. Or it can be protons or galactic cosmic rays that cause single-event upsets, and en masse, the lot of them, cause radiation damage to the solar panels and other systems. So it's very, very important for the satellite community to have the best, the most timely information that they can get. And that's the purpose of this activity, and I'm very happy to be here to participate in this. So I'll turn it back over to Dan for some concluding remarks.
Thank you very much, Joe. It's a delight to be able to tell you that we turned on our instruments and we saw fascinating new phenomena in the Earth's vicinity driven by solar disturbances. It's also a delight to be able to tell you that we are really able to do so much research with our basic research, astrophysical research, if you would say, in our local neighborhood. But it's wonderful to be part of a field where that research also has good practical applicability. And we know that the things that we're measuring now have the kind of relevance to society that Joe's spoken about. So we're delighted to try to answer any questions you may have today and to talk about this duality in our field, great basic research and also great applicability to societal needs. Thank you very much.
Okay, thank you, Dan, and thank you to all the panelists. We'll take questions now from media in the audience, on the phone lines, and then also from you all watching online. As a reminder, you can ask a question via Twitter by just using this hashtag, AskNASA. If you have a question in the audience, please get to one of the people with the microphones over here. We did receive a question or two before the briefing, so let me just throw that out to begin with. First question, what has this third Van Allen belt been doing since you first observed it last year?
Well, I can try to answer that question a bit. We saw this phenomenon for about 4 weeks. Then, as the data showed, and as Nicky remarked on as well, it was cut off like a knife edge. It disappeared. There was a rebuilding of the Van Allen belts also in a very abrupt fashion on about the 9th or 10th of October. But since that time, we've not seen a recurrence of the third belt. We're watching with eagle eyes to see if there is a resurgence of this. But so far in the last 5 months, there really hasn't been a recurrence of that.
Okay, and I guess we have some questions already via Twitter.
Yes, I read that CRES saw a third ring in 1990 and solar activity in 1998 made a brief third ring. Is this really the first time we've seen a third ring?
The CRES was the mission that was mentioned back in 1991, and that showed a new population of particles injected into much deeper into the magnetosphere, into more or less the inner zone and slot region. This is the first time that reported in the literature that one has really seen embedded in this outer part of the Van Allen zone the storage kind of phenomenon. And so we believe that this is fundamentally different than what's been reported in previous kind of observations back in the past.
Okay, is another question from Twitter?
Yes. Which belt was actually new? Was the original outer belt, did it shrink back into a storage ring and then a new belt form outside of that?
Well, let me again try. We're still trying to piece together exactly what happened, but yes, it seems as though an entire outer Van Allen belt acceleration event occurred, and then part of it was sort of ripped away, was torn away from the outermost part, leaving the storage ring, and that's what persisted, so immune apparently to external forcing for the next 4 weeks. And so what we were really seeing was that the storage ring was the remnant of an earlier acceleration event due to the kind of solar drivers that Mona and Nicky talked about.
Let me add to that also, if I may. This is still early days, and so we don't completely understand this phenomena that we're seeing. We're modeling it now. We're trying to develop the understanding. We're looking, as Nicky mentioned earlier, at the wave instruments because they are likely one of the drivers, the waves that are generated. And it's all driven by the sun, but then there are internal waves that are generated as well. We're trying to piece this all together right now, and stay tuned. We will know more.
That's really what's exciting about new observations is that when you know you've done something right observationally, when theoreticians say, well, that doesn't look right, we've got to go back to the drawing board here.
Okay, and one other question from Twitter before we go to the media.
A two-pronged question. What does the third ring mean for astronauts and satellites, and also what impact will it have, if any, on the Earth?
Oh, we might let Joe take part of that question, Joe.
Yeah, I think it probably will have little impact on astronauts and satellites, given the characteristics. But I would hurry up to say that there's still a lot that we don't know, and we can talk about space operations of today, but also there's operations in the future that are planned. So I think probably the true answer to the question is still to be known.
Yeah, and if you remember the picture that I showed during my presentation, the International Space Station is down below the inner belt. This new ring is actually much further out than that. It's at about 12,000 miles above the surface, so it's much higher than astronauts go. Now, if we send another mission to the moon or to Mars, then we would have to pass through the region. But we've done that before, too, in the past with Apollo. We passed through pretty quickly. So, but in realistic terms, it's not going to affect our astronauts, certainly not on the space station.
Okay, another.
But having said that, the regions that we're looking at with the third belt are magnetically connected to the altitudes that the space station is orbiting on. So while there's no direct impact, there are still going to be effects that are seen, and I think that just understanding more about the outer radiation belt, its structure and its dynamics are very important for enabling us to have better models, better prediction models, do a better job of predicting the lifetime of spacecraft just by knowing that it's way more dynamic than we had even expected prior to the launch.
I'd like to jump in on this and just say, too, that we're fortunate that nature performed an active experiment for us that really gave us this very kind of discrete onset and then a very discrete end to this particular three-belt phenomenon. And this is going to teach us a lot about how effectively the magnetosphere can store and maintain an electron population for extended periods of time. And by doing that, I think it's going to greatly help us greatly increase our understanding of just how this complex accelerator that Nicky talked about really operates.
Okay, our next question.
Do you have an estimate of how the total energy content of the three, then two belts changed during the process?
Let me first say that I want to emphasize what Mona said, too, which is that we're just studying these things now. Many of the questions that are being asked are exactly in our minds, and we're going to try to more quantitatively address those. So this is relatively early in the mission. We're trying to piece together what happened, why did it happen, and what are the implications for such things as total energy content.
Okay, our next question, still from Twitter.
How did this radiation belt go undetected for so long?
We've never had the capability and the outstanding technology that we have with the radiation belt storm probes, the Van Allen probes, I'm sorry. It is a mission that is designed to go after the dynamics and the structure of the radiation belts. We're carrying the right instruments and we're in the right orbit to be able to do that. And I think the fact that we've had such an amazing discovery within days of turning on the instruments is really proving just how spectacular the science from the Van Allen probes will be.
I like to quote America's most notable philosopher, Yogi Berra, who said you can observe a lot just by looking. And I believe that when you open new eyes on the universe, you invariably see new things. And so I think that's where we find ourselves now.
Okay, our next question, please.
Question for Joe Conscious. What can operators and companies do in order to protect their satellites once they have the predictions?
Well, that's a good question because it depends a lot on the particulars of the mission and what they're trying to do. But I can give you an example from the past. In 2006, the EUMETSAT, the European Meteorological Satellite Organization, launched a satellite called METOP. And METOP had on board two high-rate transmitters to send down broadcast direct TV-like imagery of the weather, and they really wanted to do it over Northern Europe. Shortly after the launch, they found that one of their transmitters quickly failed. Unfortunately, they had a backup on board, but before they turned the backup on, they wanted to figure out what the problem was in terms of the environment or exactly what. So they went back to the engineering lab and they found out that this particular piece of equipment had a susceptibility to charged particles that had a prevalence in the auroral zone and in the South Atlantic anomaly. So when they turned the backup transmitter on, they then organized or created a procedure through which they turn it off as it flies through the auroral zones, and they also turn it off when it flies through the South Atlantic anomaly, but then they turn it on the rest of the time. And in particular, they're able to capture the weather imagery from Europe, which at times is right on the edge between the auroral zone and the safe places. So depending on the kinds of activities and the particulars of the spacecraft, there are things that can be done to respond to the current state of the space weather. I don't want to say that every satellite works like this. There's a little bit of the three little pigs philosophy in building satellites. You can build your satellite out of bricks and you don't have to worry about anything. Well, that can be costly and heavy, and maybe you wouldn't be able to get the payload that you'd want at every point. So to then go to the less robust state, you may have to drive it a little bit, and many satellite operators will do that. They will reschedule command sequences. They will do the things that are at their disposal to account for harsh radiation conditions that can occur from time to time.
Okay, our next question, please.
Dr. Baker, could you briefly describe any innovations that improved the sensitivity and capability of the REPT device?
Yes, we tried to build with detectors that were more stable and more sensitive to charge deposition from the detected particles. We tried to build much faster electronics so we could avoid traditional problems of pileup and dead time and other such effects. But we really were primarily focused on being able to do a better job of resolving to a high precision the energy spectra at these higher energies. Many previous measurements have sort of just made very broad brush kind of measurements at the higher energies. And without the kind of energy resolution that we were able to achieve with the REPT instrument, I think we would have again probably sort of smooshed all this out, and we wouldn't have really seen so clearly at all that we had these kind of distinct spatial and temporal features.
Okay, next question, please.
Are the collapse of the outer belt and its re-energization connected with any external phenomena that you can identify?
Yes, I think all of us in a way have addressed that, but we see very clearly, and maybe more clearly than we ever imagined we could with the Living with a Star program. We're able to watch the ultimate driver, the sun. We can watch these things propagate through the interplanetary medium. We can then observe directly the effects with the radiation belt storm probes, the consequences in the radiation belt. So we're in an enviable time here where we can really watch cause and effect play out before our eyes. Maybe Mona or Nikki would like to comment.
We have seen in the past, when we've had coronal mass ejections, we have seen a drainage and then a repopulation of the belts. We've seen that before. That's pretty well established. What we haven't seen before is those from the original particles in the outer belt coming in and forming this storage ring or this extra area and then lasting for a month. That we've never seen before. But we pretty well understand, at least at some level, the process that happens to drain the belts originally and then refill them.
But the fact that very similar solar drivers can have such a different effect on the radiation belts is really the central focus of the Van Allen probes. Just, sometimes it does bring up the radiation belts, and other times it just annihilates them, as you saw in the plots that Dan had. And I think that now we've got the ability to really bring those outer belts into focus, as Dan said, with the new technology. What we saw before as kind of a fuzzy image, we're now seeing with great clarity.
I think since we're talking in fairy tales, the three little pigs, well, we can also talk about Goldilocks and having the sort of the right intense enough, but not too intense, so you don't completely eradicate the outer Van Allen belt, but you eradicate a portion of it. I don't think we'd really suspected before that there could be this kind of Goldilocks event that would lead to this storage ring phenomenon.
Okay, next question.
Could the probes themselves affect the radiation belts, for instance, by generating waves?
No, the spacecraft themselves will not affect the radiation belts.
Only very locally, possibly, but
very
it's pretty unlikely that that would have much effect.
Okay, next question.
Do any of the Van Allen belts intersect the Lagrangian points?
No.
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 Our simplest answer so far.
We all agreed.
We're all agreed.
Okay, I think that's all the questions we have online. Thank you for asking the questions. Thank you to our panelists. And you can follow along what's going on with the Van Allen probe mission online at www.nasa.gov/Van Allen probes. And you can keep up with all the different NASA scientific findings through our social media channels. We've got quite a wide array from them. There's always something amazing happening at NASA. Again, thanks everyone for watching. Have a good day.